Right, hello there. This video has a look at reacting mass calculation. So what I'm going to cover with you is how you can use a balanced chemical equation to predict the maximum mass of product you might get from a chemical reaction or the minimum mass of reactants that you would need. And I'll cover a little bit later on why I'm using those words maximum and minimum. Now, this is primarily aimed at GCSE students. It's useful for A-level students as well. If you're doing this at A-level, please use the AR relative atomic mass values to one decimal place from your periodic table. And you will need a periodic table and a calculator. So a typical question, calculate the maximum mass of carbon dioxide produced when 32.0 grams of methane undergoes complete combustion. Now I say the maximum mass because there's all sorts of reasons why a chemical reaction might not give 100% yield. Now, the first thing to do is to scaffold our answer. So let's do this now. So two boxes there, one for methane and one for carbon dioxide, because those are the two chemicals that are mentioned in the question. Now, I've got a mass of methane. What I've got to do is convert that into moles. Remember, moles is mass divided by MR. So I've got 32.0 grams. Now the MR of methane, the relative formula mass, CH4. Our relative atomic mass for carbon is 12, and we've got 4 hydrogens each with a relative atomic mass of 1. So therefore our relative formula mass for methane is 16. Now 32.0 divided by 16 gives us exactly 2.00 moles. Now, good practice to record the numbers of moles to 3 significant figures, but when we're doing these calculations, please keep the full precision value in your calculator and only do rounding at the end. Now, if we've got 2.00 moles of methane, we're going to get 2.00 moles of carbon dioxide because we've got a 1-to-1 ratio. Remember, we don't bother to write ones as balancing numbers in chemistry, but you need to appreciate that they're there. So we can write here 2.00 moles. Now, the question is, what's the mass of 2.00 moles of carbon dioxide? Well, think about the equation number of moles equals mass over MR, the relative formula mass. Well, mass is therefore number of moles times by the MR. So we need to know the MR of carbon dioxide. Now, carbon is 12, and we've got 2 oxygens, each of which are 16. So therefore we get an MR of 44. So mass, number of moles times by MR, so we've got 2.00 times by 44, and we get 88 grams. Good idea just to underline the answer and make it stand out and easy to see and easy to mark. Okay, if I move on to another calculation now. So what mass of potassium is needed to produce 28.0 grams of potassium hydroxide? So like before, I'm going to scaffold my answer. Now, the question gives us a mass of potassium hydroxide. Therefore, we need to start with this side of the equation first. Now remember, number of moles is mass divided by MR. So 28.0, and we need to know the MR of potassium hydroxide. Now, potassium is 39, oxygen is 16, and hydrogen is 1. So therefore the MR is 56. So 28.0 divided by 56 is 0.500 moles. Now, that's exactly 0.5. Remember, leave the full precision number of moles in your calculator for your calculation, but record your numbers of moles to 3 significant figures. Now, the question we need to ask ourselves is how many moles of potassium do we need? Well, if we look at the equation, we've got a 2 to 2 ratio here. That's the same as a 1 to 1 ratio. Therefore, we need 0.500 moles of potassium. So 0.500 moles. Now, the question we need to think about is what is the mass of 0.500 moles of potassium? Remember, mass is number of moles times by the MR, or the AR, in this case, the relative atomic mass. So we need 0.500 times by 39, and therefore we get 19.5 grams. Once again, underline it and make that a little bit easier for whoever's marking it. Now, that would be the minimum mass of potassium you would need to produce 28.0 grams of potassium hydroxide. Okay, so let's move on. Calculate the mass of oxygen gas needed to burn 10.0 grams of hydrogen gas. So once again, let's scaffold the answer space. So we've got a mass of hydrogen. So what we're going to do is work out the number of moles of hydrogen. Remember, number of moles is mass divided by the MR, so 10.0. And because it's H2, the formula, we divide by 2, and therefore we get 5.00 moles. Now, we need to work out the number of moles of oxygen gas that are required. So let's put an arrow up to oxygen. Now, in this case, we've got a 2 to 1 ratio. So to burn 5.00 moles of hydrogen, we need 2.50 moles of oxygen gas. Now, we need to work out the mass of oxygen gas, and mass is number of moles times by MR. So 2.50 times by, now oxygen, the AR is 16, the relative atomic mass, so 16 plus 16 is 32. So 2.50 times by 32. So let me put that in my calculator, and we get 80.0 grams. So let's give that an underline so it just stands out a little bit. And there we go. So moving on. Now finally, calculate the maximum mass of titanium that can be extracted from 3,800 tonnes of titanium chloride. Now, some exam questions will tell you how many grams in a tonne, so you might get this information. My advice to you would be ignore that, and to do the calculation as if you had 3,800 grams of titanium chloride, then all you need to do is change the units at the end. That's the way I'm going to do it. So once again, let me scaffold the answer space. So the question's given us a mass of titanium chloride. So moles is mass divided by MR. So 3,800 divided by the MR of TiCl4. Now looking at my periodic table, titanium is 48. And we've got 4 chlorines, each of which are 35.5. So that gives us an MR, a relative formula mass of 190. So 3,800 divided by 190 gives us 20.0 moles. Now, how many moles of titanium are we going to get, or what's the maximum number of moles of titanium? Well, no balancing numbers here. It's a 1 to 1 ratio, so therefore 20.0 moles of titanium. So what we need to do is get 20.0 and multiply it by the AR of titanium, which is 48. And 20 multiplied by 48 is 960. Now remember, our question mentioned 3,800 tonnes, so therefore our answer is 960 tonnes here. I just underline that and make it really easy to see. And that's the maximum mass of titanium that you can get from 3,800 tonnes of titanium chloride. Okay, so that's reacting mass calculations, hopefully made simple. Thanks for listening.